So section 14.3, we're going to be talking about one-sided limits, continuous functions, and kind of more to the point, what it means for a limit to exist. So we make these kind of distinctions, and we've seen it before with some of the piecewise functions that we've dealt with, is sometimes if we approach a limit from the left-hand side, it's not always the same value as we get from the right-hand side. So how do we differentiate between the left and the right? Well, we use this notation, and I'll just zoom in just a little bit so you can see. So the limit as x approaches c from the left, which means if I look at this graph, I'm coming from the left and I'm getting closer and closer to some value from the left. So I'm coming from the negative, I'm getting closer and closer to some value here. So when you see this notation, from the left, we read this as the limit is f of x as x approaches c from the left. And if you need to, you can look at your hands. The one that makes an L is your left. So that's where you're coming from. Likewise, if we have this notation as x approaches c with a plus sign, we read that as the limit of f of x as x approaches c from the right. So we're coming from the positive numbers. So if we look at this picture here, we're coming from the right. So some value x, and we're approaching c, we're getting closer and closer from the right. We're coming from the right. If we have these two things, one of the facts that we've been dancing around is this theorem. So suppose that the limit, the left hand, so we call this limit from the left, we call that the left hand limit. And this one from the right, obviously we're going to call that the right hand limit. So suppose we look at the limit from the left and the limit from the right. Then we say the limit of f, the limit exists if and only if the left-hand limit is equal to the right-hand limit. Furthermore, it says if the left and the right are equal, then that's what the limit is equal to. So what does this mean? In order for a limit to exist for a function, the left-hand limit has to be equal to the right-hand limit. Okay, let's try at least one of these problems out. And sorry for the formatting issue. Should be on the next page. So, we want the limit as x approaches 2 from the left. So this is our left one. This is our right one. If I look at this function here, and what we can do is we can easily draw a graph. Graphs are our friends. So 2x minus 1 for x is less than 2. 2x minus 1. So the intercept is, let's plug in 2. The intercept is negative 1. And we go up 2, over 1, up 2, over 1. And we're less than, so we're open dot. So there's our first part. We are 1 when x is equal to 2. So y is 1 when x is equal to 2. So there's our closed dot there. And then x minus 2 for x is greater than 2. Okay, so if I plugged in 2 here, I get 0. If I plugged in 3 here, I get 1. So I get this kind of line. Okay, this is what our function is. So if we're approaching 2 from the left, so from the left, we're getting closer and closer and closer to this value right here, which is 1, 2, 3. So our left-handed limit is just equal to 3. We're getting closer and closer and closer to 3. From the right, we're getting closer and closer and closer to 0. So the left-hand limit, so as x approaches 2 from the right, is equal to 0. Now, the limit as x approaches 2 from either side, in order for this to exist, these two have to be equal to each other. So we write DNE, or does not exist. All right, moving on. So sorry about the formatting issue. This should say continuity of a function. So with the continuity of a function, remember what we said earlier in pre-calculus. We said that a function is continuous if you don't have to pick up your pencil to draw it. So it passes the pencil test. That's what we called it. And we couldn't really define that any more clearly than just the pencil test. Makes sense. You can understand that as a 9th grader, what it means to pass the pencil test. So let's just take a look at some of these graphs, see which one's continuous and which one's not. So A is continuous. B has a jump. C has a hole. So we have to pick up our pencil because we can't be at that point. At D, we also have a jump discontinuity because we have to pick up our pencil and write it down. Same thing with E, we have a jump discontinuity, or so here, all of these, when I have to pick up my pencil, these are not continuous. So the only continuous function is A. All these other functions are not. And what we're going to do is we're going to define continuity using limits. So the three things in order for something to be continuous at every single point. So at any point C. So we want C to be in the domain of F. That's important. If C is not in the domain, then it's not going to be continuous. The second thing, we want the limit as x approaches C from the left to be equal to f of C, and we want the limit as x approaches C from the right to be the same value. So in other words, if the left-hand side and the right-hand side are equal to the same value, then we know that the limit exists. So in other words, a function of f is continuous if the limit exists. Okay. So let's try this continuity thing out on the next example. So let's take a look at example 2. First thing, we want to determine the numbers at which this function r is continuous. So if I zoom in just a little bit, we need to know what the domain of this function is. So we first need to factor the denominator. To find the domain of a rational function, that should be x minus 4, x minus 2. So for part A, and I'll just write it up here, my domain is all numbers x such that x is not equal to 4 and x is not equal to 2. That's how we write this domain out, using a set notation, which we have been doing for a little while, so I think we are more comfortable seeing this. What this also means is what's numbers are not in the domain, 4 and 2. So we say, where is this continuous? It's continuous at all points except x equals 4 and x equals 2. So that's where we are continuous. So that means this is a discontinuous function. So we're going to have to figure out where those discontinuities are. So that brings us to B. Use limits to analyze the graph near 2 and near 4. So we're going to first say, what is the limit as x approaches 2 of my function? And I'm going to write it out in factored form. So x minus 4, x minus 2. Now here, if I plug in 2 right away, I get 0 over 0. So I'm going to simplify this function. So I'm left with 1 over x minus 4. And we want the limit as x approaches 2. It's important to keep writing that. And I certainly slack on that. So if I plug in 2 here, I get 1 over 2 minus 4, so negative 1/2. Which means, even though I get a discontinuity if I get a discontinuity at 2, but I get a value out, I have a hole in my graph. So that just means, just like we had over here, we just have a hole in our graph. It's getting closer and closer from each side, but we're not a value there. And the whole goal is to actually build this graph. So, next up, we're going to look at the limit as x approaches 4, and I'm just going to go straight to the simplified version of 1 over x minus 4. Because if you plug in 4 here, you get 0 or 2 over 0. So using our simplified form, this is going to get 1 over 0. So this is, normally we would say that's undefined. But we can use what we've been talking about. The limit as x approaches 4 from the left of 1 over x minus 4. And if we think about this, if we pick a number to the left of 4, let's say negative 3, or let's say 3, or 0, we're going to get a negative number. And if we get closer and closer and closer to negative 4, or to 4, we're going to get more and more negative. So, this is going towards negative infinity. Likewise, if we looked at the limit as x approaches 4 from the right of 1 over x minus 4, we're getting closer and closer and closer to 4, but these numbers are positive. So that's getting closer and closer and closer to positive infinity. So if we have from the left, this is the left, and this is the right, one's going to negative infinity, the other's going to positive infinity. Right here, we have a vertical asymptote. And this is where that concept comes from. We have a split from the limits from either the left or the right-hand side. So the last part is, let's draw a graph of this. So, with our graph of R, I'm going to skew this just a little bit. We know we're basically graphing 1 over x minus 4 in our simplified version with a hole at 2. So I can go 1, 2, 3, 4. At 2, we know that the y value is negative 1/2. And here, if we take it out to infinity, we also know that there is a horizontal asymptote at 0. So what our graph looks like is getting, from the left, it's going down to negative infinity. From the right, it's going up to positive infinity. So if we just look at all of this information that we figured out, it's undefined at 4. From the left, it's going down to negative infinity. From the right, it's going up to positive infinity. Now, the other two, the last piece, this horizontal asymptote, is more so asking, what's the limit as x approaches infinity or negative infinity? And we'll talk more about that when we get to calculus. So let's try one more question, and we're going to graph it first, and then we'll be done. So example 3, we want to determine the numbers at which the following function is continuous. So let's first graph this function and see what it looks like, because I think it's going to be easier than most. So we look at our piecewise function. X squared when x is less than 0, less than or equal to. So we can put a dot there, and we can graph our x squared graph. X plus 1 between 0 and 2. So between 0 and 2, I have, if I plug in 0, I get 1. So that's an open circle. And if I go out to 2, that is 3. And that's another open circle. Okay? So we see that it's already discontinuous. So we want to figure out where it is continuous. And, if we can, figure out what kind of discontinuity we have. The last one, 5 minus x for 2 to 5. So if I plug in 2, I get 5 minus 2 is 3. So at 2, we are at 3. So these share a common point. 3, 4, 5. If I plug in 5, I get 0. So here, where am I continuous? Looking at the graph, it's continuous everywhere but x equals 0. Or it's discontinuous at x equals 0. Now, why is that? If we did the limit as x approaches 0 from the left, we're getting closer and closer to 0. If we did the limit as x approaches 0 from the right, we would get closer and closer to 1. These are not equal to each other. Not equal to each other. Likewise, if we looked at the other transition point at 2, if we did the limit as x approaches 2 from the left, we see that we're getting closer and closer to 3. Same thing. The limit as x approaches 2 from the right, we see that we're getting closer and closer to 3. Because these are equal to each other, then this is continuous. So that's using limits to justify the graph. We will go over any questions you guys have on this topic in class, and hopefully, if we have time, we'll get to 14.4.